Hi, my name is David, and this is Group 7, and this is our project High Power. So the first thing I want to talk about is the needs and abilities of Sparkville. And first thing I want to talk about is that Sparkville needs to be able to produce and deliver consistent, measurable power, and it also needs to be cost efficient, needs to be portable and freestanding, while also conforming to the environment and following specific design specifications. And next, as you can see, this is our decision matrix, and we use this to pick our final build. And how we did that was we created a list of certain criteria, which was projected efficiency, cost, and also design difficulty. And the highest score was our ramp, and that's the final design that we chose.
Hello, I'm Joseph Leonard, and I will be talking to you about our designs. Our first design incorporated a very large tank. We tried to simulate a dam, and to generate water pressure, we were going to just build up that water in that tank. But that was a very heavy unit and was not that portable. So we did do some variation while trying to keep the potential energy. That's what we were actually after, not so much the amount of water it contained. So we did that by posting the cone up on those stilts rather than that tank above the water wheel. And what that allows is that we do lose that volume, so it does become more portable, and we maintain that potential energy constant. And real quick, I just want to touch briefly on our pulley system that we have. We do have that water wheel mounted between those two supports, as you can see on the right, and that is directly hooked up to the generator via a pulley. In our third design, I should say, this we completely did away with the cone, and we just elevated a smaller tank to maintain that potential energy constant and be able to move that generator off the ground. But we found, once we went through our Bernoulli's equation, that we got a water flow of 8.02 feet per second out of the drain of that last design. And that was losing the potential energy of the spout because it was 6 inches above our allocated build height, and we were losing kinetic energy. So with that in mind, we did decide to do this ramp instead. This ramp would maximize the amount of water that was able to fall and travel in the horizontal direction onto our water wheel. And the water wheel design, and real quick, the pulley design, we did totally change this. We pushed the water wheel off the side, and then we put some supports on to counterlever that, and then the pulley for the water wheel is a separate mechanism with a 10-to-1 ratio going back to the generator. The water wheel itself, well, here's the design real briefly. As we went through the stages and building, and we did end up putting in a second support for our ramp once we developed it further. These are our final specifications for our build. Like I said, we did add that second support, and our water wheel is a little bit different than standard water wheels, and Turkey here will be more than happy to tell you about that.
Hello, I am Turkey, and I'm going to be explaining our overshot wheel and why we chose this kind of design. So the reason we chose this wheel is that for two reasons. The first reason is that the mechanical efficiency, and the second reason is it is easy to maintain, basically easy maintenance. And as you can see, the fins are not flat, they are curved, which is easier for the water to flow. And that gives us more efficiency, and the mechanical efficiency ranges between 70 and 80%, which is ideal for the design we are working on. And now,
Hi, I'm Abraham, and I'm going to talk about the power for our generator. So, plotting the stall torque against the no load speed of our generator, we get this power curve. And in order to find the amount of theoretical power that we can produce at a certain point of an angular speed, you would find the area underneath that point, as shown here. This is the theoretical power that we can create at this speed. I mean, this is a bit higher than what we actually did in testing, mostly because of friction and other factors, but that's what we're showing here. This is our list of materials. Not too much to say here. We did come in under budget, both in our own projected budget as well as Sparkyville's budget overall. So showing the cost effectiveness of our design. In conclusion, we solved the main problems of Sparkyville, which is consistent power. We used the space given, we didn't go over. We came in under budget, pretty far under budget, as seen here, 27%. And the predicted store based on our design, our budget, our constraints, our output, theoretical as well as actual in our testing, we predict a score of 25 out of 30. Thank you very much.
All right, thank you guys. It's uploaded.
Pause on to that.